Today we are going to be talking about converting all the words in a corpus into vectors. This is going to be a very important topic for all the lectures that we are going to be hearing from now onwards. So, before getting into the detail, let me first recap of what we have done earlier. In the earlier classes, we saw why NLP is hard. We gave some examples in terms of sentences, and we wanted those sentences to be converted into a form that can be understood by the machine. So, even for a human, it's going to be very hard for to understand certain sentences. So, how are you going to make the machine to understand some sentences which are even hard for humans? So, we mentioned that it was pretty hard. So, this NLP is a very hard problem, and then we started looking at the various corpus that was available to us with respect to the terms or the word frequencies. We actually counted how many words are present in a given document, and then we introduced the term inverse document frequency. And then we actually introduced some empirical formula or the laws that gave us some prediction in terms of the vocabulary when you given the corpus using the Heap's law. And then Zipf's law gave us some ideas in terms of the kind of frequency distribution of every word in an empirical way. And then we also looked at another type token ratio, which measured the lexical density of a given corpus, using which you can find out what kind of vocabulary or how rich that particular document or the corpus is with respect to the vocabulary in English. And then we brought in one interesting concept by converting all the documents into a binary format. That means every word present in a document is given a binary value, either it is present or not present, and then we constructed one binary incident matrix for the whole corpus, and then we try to apply some binary rules for information retrieval. And you know well that when you use a binary operations, it is not possible for you to rank the document within a corpus. So, we brought in the idea of TF-IDF and how TF-IDF could be used to rank those documents. So, you must have understood by now we are looking at the corpus in terms of the data that is present inside with respect to the frequency of the words, and then trying to find out how those frequencies could be used to retrieve the documents in the given corpus, given a query, and so on. So, this is going to be the path that we are going to follow throughout this course, where we will be looking at the documents with respect to the data. That means the whole approach is going to be data driven. That means we are not going to be using a lot of linguistic ideas into this. We will be using a lot of statistics and probability ideas into the document, and then see how those things could help us in terms of understanding a document. You are also aware at this point in time that the idea of the entire exercise is to find the meaning of the word. So, we so far have not come to that level. So, we are now in the progression towards understanding the meaning of the word from the corpus without really looking at the dictionary and so on. So, we will get to that part little later, but today we will focus mainly in terms of how do I really convert those words into vectors, and then how do I use that are available in the vector algebra to retrieve documents and do certain other operations and so on. Okay. So, what I will be doing today in this lecture is I will just introduce the basic concept of the vector space. I am sure some of you are aware of this. For those who are not familiar with this, I will just give a few minutes introduction to 2-dimensional vector space and 3-dimensional vector space and what we represent in these spaces. And then we try to map those vector space into the words and documents, and how we actually map words as axis in the vector space, and then how do we represent a document as a point in the vector space which contains a lot of terms and so on. Okay. And then we will bring in the concept of query modeling, and then later we will talk about how do we really find out whether documents are similar. If, for example, if you have multiple documents in the given corpus, you want to find out the closeness of one document with the other. So, we have some measures that we will introduce in this class, and then we will also mention what could be the suitable measure if you want to find the document similarity. We will look at one of the demos in the document similarity, that would be on cosine similarity, and then we will introduce what is a word vector really, and then represent them in terms of a one hot vector, and then later we will bring in the concept of how do we represent relationship among the terms with respect to either relationship or some composition based operations and so on. And finally, we will show one example of why this could be useful in terms of named entity extraction using the information extraction model. Okay. So, let us move on to the first slide in this exercise, which is about two-dimensional vector space. Two-dimensional vector space is defined as a set of linearly independent basis vectors with two axes. Each axis corresponds to a dimension in the vector space. So, if you look at the diagram here, so we have linearly independent vectors x and y. Okay. So, what that means is any operation that you perform using this particular linear basis vector will not result in a value, it will always result in a null value. That means they are in the vector space time, they are orthogonal to each other, they are in this fashion. Okay. So, if you want to represent a point which corresponds to both these axes, we just find out what is the value of that point with respect to the x axis and y axis, and then mark that point. So, that let us call that as a point P, which measures x from the x in the x direction and then y in the y direction. Okay. And then next what we are going to do is we are going to define a vector. You probably familiar with this vector is going to give you the position as well as the direction. So, now if you connect the 0 0 to the point, and then now it has a direction attached to it, this is a vector. So, now P becomes a vector in this space. So, extending this to the third dimension, we have one more axis is z here, and then the same notation that I am using, a point is represented as 3 variables here x, y and z, and then the vector in the 3 dimension is mentioned here. Okay. So, that means if you are standing in front of a corner of the 3 walls, right, and then your x, y, z would be here somewhere, right. So, again if you look at this, all these basis vectors are independent, and any vector operation, for example, a dot product of x and y or x and z would result in a 0 value. So, we are going to map the same space vector space for words and then see how it looks. So, now let us assume that all the words in the corpus are considered as linearly independent basis vectors. That means every word is different, they are not connected to any other word. Suppose if you are having about 300 words, all 300 words are independent and they have no relationship to each other. That means if I do a dot product of a word A and B, that means the result would be going to be 0. So, again we will be using the notation of V. This is the length of your vocabulary. If you consider all of them as linear, and then all the vectors related to the words in the vocabulary are linearly independent, and they do not have any relationship with each other, and they are represented in the continuous vector space R. Okay. So, as I mentioned earlier, again like in the case where I have introduced the vector space, every word now represents an axis. Okay. So, earlier we had x and y for the namesake. Now, we are going to be representing them with respect to words. Every word will occupy one axis. So, that means if you have the size as v, that means we are going to have v axis in that particular vector space. I am giving two examples here. I am sure you know that the vocabulary of any language is more than 10,000. In the case of English, it is more than a million. So, for example, if you take one corpus and then find out what is the vocabulary within that corpus, you will have some number. For example, if you take the EMMA corpus given from the NLTK platform, it is going to be about 7079. That means there is going to be 7079 axes in that vector space. It is very hard to imagine beyond 3, but this is how it is going to be in the natural language processing if you want to represent all the words in terms of axes. If you look at the Google News corpus, it contains about 3 million words. That means we are going to have 3 million axes in that real space of R. So, it is very huge, it is very huge, and it is very difficult to imagine that kind of access for many of us. Okay. So, how do I represent the documents? Okay. So, now we know that every word is representing one axis. So, where is the document coming into play? So, you know that document contains a lot of terms, right. Here again I am repeating, the terms are either words or the combination of words or phrases. Okay. So, we will be using terms in general in most of the cases here. So, the document that we are talking about now contains lots of terms, correct. So, that means a document is a point in that vector space occupied by the vectors of words in that particular document. Suppose if the document contains about 100 words, that means a document is represented by those 100 points in that space. Okay. So, I mentioned already that combination of the terms represent a document vector in that particular vector space. It is going to be very highly dimensional, and it is going to be very hard to really look at it from the two-dimensional display that we have. So, what I am going to do is I am going to just take a simple example where there are only 3 documents, and these 3 documents are going to contain words which are car, good and mechanic. Okay. That means good is represented in this axis, car in the usual y axis, and then mechanic in the usual z axis or z axis. Okay. And we have 3 documents here. The document 1 contains all 3 words, document 2 contains only good and mechanic, document 3 contains car and mechanic. So, if you want to represent the document 1 in that 3-dimensional space, it is going to be here, right. And then if you want to represent good and mechanic, so it is going to be in this between these 2 axes, good and mechanic here, and then car and mechanics in this space, correct. So, now we actually created a binary incident matrix for all of those and then represented them in the 3-dimensional space. In general, these words are represented using TF-IDF. Okay. So, what we are going to be doing is we are going to be representing them in terms of these values of these vectors. So, this is your document vector, okay, and this is your word vector for all the documents in that space. So, let me see how we can represent those documents. See, if you look at carefully the the right hand side of this slide, we have document 1 having the word good and mechanic, document 2 again having good and mechanic, document 3 is again having good and mechanic. That means I am going to only look at this particular axis, okay, for our representation of these documents. So, now document 1 is very close to the good axis, right. So, if you look at the value of document 1, it is pretty high when compared to what you have for mechanic. That means there is a good alignment of this document closer to the axis good rather than to the other space, but it is represented in that 2-dimensional space which is marked here. Okay. So, I can represent a document 3. Again, if you look at document 3, it is pretty close to mechanic than to the axis good, maybe because there are more number of terms that are representing mechanic than good in this case. So, that is why D3 is pretty close to mechanic. And then if you look at D2, which has a fair amount of representation from good as well as from mechanics, that is why it is somewhere in the middle. So, this is the actual space that we are looking at, and all the documents that contain those 2 words would be represented in this space, okay. And the length of that particular document depends on how those frequencies are distributed in the document.